consider a linear programming problem. So your problem is minimize 3x1 plus 2x2 subject to constraints x1 plus x2 greater than or equal to 2, x1 plus 3x2 less than or equal to 3, x1 minus x2 equal to 1. Okay, so this is my linear programming problem. Okay, so first what we do is convert to standard form. Okay, so what is my standard form here is my first constraint is greater than type, so I will be having what, x1 plus x2 minus s1 is equal to 2, and in the second constraint I have x1 plus 3x2 plus another variable s2 is equal to 3, because less than type constraint I have to add slack variable. Third one is already an equality constraint, so I will leave it as it is. X1 minus x2 is equal to 1, and my objective function is what, minimize 3x1 plus 2x2, again 0s1 plus 0s2. Okay, so if we write a matrix here, so what it should be, so my columns for x1 is 1 1 1, column of x2 is 1 3 minus 1, then column of s1 is minus 1 0 0, and column of s2 is what, 0 1 0. That's it. Okay, so you see we have 3 constraints and 4 variables, right? And see, you can always see the determinant of first 3 columns if you pick up. So determinant is non-zero, so rank of a is, so you can see that rank of a is 3, so number of variables in basis is also 3, right? And we have already assumed that we are taking a full rank system in which the number of constraints is equal to the number of the is equal to the rank of the matrix. Okay, so that means out of 4 variables I have to construct a basis with 3 variables. Okay, so my question is, what are the variables in the basis? Okay, so what variables here? Okay, because if you see, we are not having an identity matrix here. So if I choose say first 3 column, what is the guarantee that if I multiply say b inverse and right hand side, and the answer will always be greater than or equal to 0? So in this situation it is really difficult to choose a basis, because हो सकता है hit and trial से that you choose first 3 variables और आपका feasible basis आ जाए, और हो नहीं भी सकता. बट ऐसी कितनी पॉसिबिलिटीज हैं? सो यू हैव 4C3, मतलब 4 पॉसिबिलिटीज हैं टोटल, या तो सारी चेक करो, बट अगेन वी डोंट वांट टू चेक ऑल दोज पॉसिबिलिटीज. ये भी पॉसिबल है कि कोई भी बेसिस फिजिबल ना हो. सो हाउ आर वी श्योर दैट माय गिवन बेसिस इज अ feasible basis? Okay, कैसे इस प्रॉब्लम को शुरू किया जाए, because we are not having identity matrix here. Okay, any idea what basis should we choose and how to do this? Okay, so
उसमें जीरो ज़्यादा.
so in the absence of identity matrix, in A, what we are going to do, we will create an artificial identity. How we are going to do this thing? Okay, so what we do, we reconsider our system. So because identity nahi hai, but only one column of identity matrix is there, that's 0 1 0. So in order to create an identity matrix, I need to have 1 0 0 and 0 1 0. Okay, so that means in first constraint and in third constraint I need to make some additions. Okay, so I rewrite my system as in this form. So I will add some artificial variables here. So add artificial variables. Okay, so what are the artificial variables? So my system will become that it is x1 plus x2 minus s1, because identity is missing from the first column, so I am adding a artificial variable xa is equal to 2. Similarly, I am adding x1 plus 3x2 plus s2 is equal to 3. There is no need to add artificial variable in second constraint because already I am having a column of the form 0 1 0. Okay, in the third constraint again, I'm missing my identity column, so I have x1 minus x2 plus and another artificial variable xv is equal to 1. Okay, so if I rewrite my system, okay, I will be coming, so please keep listening. I will be telling you all the queries. Please keep listening now. So what is this all artificial variables? What I am going to do with this thing? Okay, so you see in this case, what I have my A matrix as what my system will become like. So my A matrix will become like this. So 1 1 1 1 3 minus 1. So minus 1 0 0. Then if I am adding artificial variable, I have 1 0 0. Then again for s2 0 1 0, and for 0 0 1 I have my A matrix here. Okay, and you see I have a identity matrix here which I call as a, so after adding two artificial variables, I'm able to create an artificial identity. Okay, clear? So but the point here is I really don't want these artificial variables in my system. Why? Because you see I have a constraint, original constraint as what? See, x1 plus x2, say minus s1 equal to 2. So that means this quantity 2 has to be distributed among x1, x2, and s1. But if I'm using this constraint, that x1 plus x2 minus s1 plus xa equal to 2, that means some share of this number 2 is also distributed with xa, but xa was not a part of my original system, so it should not be there. But I have created these variables or introduced these variables just to create an identity matrix so that I can start with my simplex method. But at the same time, I really do not require these variables because they are not the part of my original system. Okay, in the standard form. Okay, so they were not part. So that means now I have to do something that I should get rid of these variables. But because I am entering into the simplex method, so once I am into the method, the algorithm will decide which variable has to come and which variable has to leave. So that means I have to train my method in such a way that these variables should take zero value. Okay, so once they take zero value, that means this number 2 is distributed among the original, which I call legitimate variables, and this number 1 should be distributed among x1 and x2, so that all the overall system of equations have a solution without these artificial variables. Okay, but for the time being, because I am taking x1 s2 s3 as an identity matrix, and initially I will have to take these variables into the bases. That means I'm putting all other variables at zero level. So it means initially I'm giving x a some value which is equal to 2. So you see here, you see how this thing is working, like from this matrix A. So my initial identity is um, see this initial identity, or I should say initial basis, is what it will comprise of the variables. Which variables? Like xa, s2, and xp. So if you look at the column, so this is x1, x2, s1, xa, s2, and xp. I have written these columns according to their to these variables. Okay, so if I am taking initially these three variables in the basis, and corresponding to these three variables I am having I am having an identity matrix. So I say my B is identity matrix, And I have seen that once I have an identity matrix, it is very easy to create first simplex table. So what is my simplex table here in this case? So what you do, you see, this will be your table. So I'm taking in my basis what, XA, S2, and XB, right? Okay. And because my initial B is identity, so same as B inverse. So what is my first column? It is B inverse, the first column A1. So my first table will be what, same, because I'm using the identity matrix. So my columns are X1, X2, S1, say A, XA, S2, XB. Okay. So my second column will be as it is, because when I multiply B inverse A2, it will be same thing, 1, 3, minus 1. So it will be 1, 3, minus 1. Similarly, my third column will be same. My fourth column will be what, 1, 0, 0, 0, 1, 0, 0, 0, 1. And your right hand side is what? Right hand side is 2, 3, 1. Okay, so I have created a basic feasible, so-called basic feasible solution with the help of artificial variable. But again, since I really do not want these variables to have positive values, I just created these variables to for the sake of making my initial table and just to start my simplex method. But now I should make sure that these variables must leave the basis, because if they leave the basis, they will become non-basic variables. And once they are non-basic variables, their values are zero. So once they have zero value, so that means my original variable x1, x2, s1, s2, out of these four variables, three variables will be here, will occupy a place in the basis, and the artificial variables are taking zero value. So means I have a feasible basic solution in terms of my original variable. But now the difficult task here is how I should make sure that my variables xa, xb should leave the basis. Okay. So for this, you see, my objective function was what? So objective function was my minimize. So I have to check from here, minimize. So minimize 3x1 plus 2x2 plus 0s1 plus 0s2. Okay, so this was my objective function. Now since I have added artificial variables, okay, so they should also have some contribution here in the objective function. And here is what going to decide what happens with the artificial variables with the proper choice of their coefficients. Okay, since the problem is minimization type, you please be careful here. And I am and I have artificial variables are also here. And since I want my variables to leave this basis, so what I am going to do, I'm going to give them a very high penalty. So what I do, I give them a very high cost, max ma, and say mxb. So here m is a very large number. It can be a very large number, as large as you can think of. Okay, so what will happen, because if m is a large number and xa and xb are having positive values, say 2 and 3, so my objective function value will be very, very large. But my simplex method will try to minimize this large value, and it will happen only when this xa and xb will have the minimum possible value, and the minimum possible value is zero. If the simplex, because simplex method has this property that it is going towards the optimal solution. So if this problem has a solution without artificial variable, I will be able to put or reduce these values to zero. Okay, so let's see what happens if I'm taking this cost as m. So objective function cost is m. What is the cost of s2 is 0. Cost of xb is also m. Okay, m is again a very large arbitrary number. So what is my zj minus cj? I can calculate here. So you can see, if I write my cj here, so the cost is 3, 2, 0, m, 0, m. Okay, so my zj minus cj is, you multiply this cb with the first column. So what is this, m plus m, 2m, 2m minus 3. And what is the second coefficient, m minus m, 0, right? 0 minus 2 is minus 2. Third one is minus m. Fourth is m minus m, 0, 0, 0. This is my solution. And what is my objective function value? You multiply CB with the XB, so it is 2m plus 1m, it is 3m. This is my objective function value. Okay, so the question is this an optimal solution, right? So you see, my Zj minus Cj's are negative, but first Zj minus Cj, so here Z1 minus C1 is equal to 2m minus 3. Okay, since m is a very large number, so 2m minus 3, 2m minus 2m is a very large number, so 2m minus 3 is a positive quantity. Okay, is a positive quantity. So but this is a minimization type problem, so in order to have an optimal solution of minimization problem, I must have Zj minus Cj all less than or equal to 0. Okay, so recall, for minimization problem, minimization problem uh, the given table depicts an optimal solution if Zj minus Cj is less than or equal to 0 for all j. Okay, but you see, for Z1 minus C1 it is strictly positive. So since Z1 minus C1 is positive, so this table is not optimal. Okay, so what we have to do, we have to enter this Z1 minus C1 into the base. So we have to enter the coefficient of the Z1 minus C1. So first variable x1 into the bases. So we enter x1 into the bases. You can see from the same formula here for minimization case that z hat is what? Z minus theta j into zj minus cj. So I want my new value should be less than z. So z hat will be less than z. Why? When this z hat will be less than z? When I will subtract a positive quantity from z. Okay, so I have to in order to subtract this quantity, because theta j is always non-negative, zj minus cj has to be positive. So z hat will be less than z if and only if zj minus cj, for whatever j, it should be what? It should be greater than 0. Okay, so in this case we have z1 minus c1 is positive, so we enter z1 the variable x1 into the bases. So x1 will enter into the bases. Okay, so if this x enters into the basis, who will leave? Again, I will go for the minimum ratio rule. So what is my minimum ratio rule? So it says that I take the ratio, it is 2 upon 1, 3 upon 1, 1 upon 1. So what is the minimum ratio? It is 1. So that means minimum ratio occurs where? Minimum ratio occurs at this column, this row. So that means my x1 will enter the basis. So that means x1 enter the basis. Okay, and xb leaves the basis. So with this choice, I will have improved value of objective function. Improved in the sense, because it is a minimization problem, my value will decrease. Okay, so what will be my next table? Again, I have to apply the same row operations as we learned in the previous classes. So what is that? So my variables are what? X1, X2, S1, XA, S2, and XB. Okay, again, I want to tell you one more thing. Because XB leaves the basis, I really do not need to calculate the column for XB anymore, because I don't want this variable to enter into the basis again. So I am moving towards a feasible solution now. The present solution with XA, XB having positive value, this is not a feasible solution for my original problem. The feasible solution for my original problem is without these variables. Okay, so let's see what is my next basis. I have xa as 2, and here I have first variable x1 that entered into the basis. So again I have to go for the simplex iteration, row operations. So I have to make this entry 1, which is already 1. So the same row remains intact what I have. For xb I'm writing 1 for the time being. Okay, now in order to make this entry 0, I have to use this pivot to make all the entries 0. So what is that pivot? So what is the row operation I am using here is that row 2 is what it is, row 2 minus row 3. So subtract row 2 row 3 from row 2. So I'm getting here 0, 4, 0, 0, 1, minus 1, and 3 minus 1, 2. Similarly, for first row again, row 1 is what? Row 1 minus row 3. So it is again 0, 2, minus 1, 1, 0, minus 1, and 2 minus 1 is 1. Okay, and in order to calculate zj minus ej, you can multiply this with 2m minus 3 and subtract it. This is one way, but I generally found it easier to calculate cb first. So cb is my m. For s2 it is 0, and the cost of x1 is 3. Okay, so what is my zj minus ej? So this is 3 minus 3 is 0. You can again write your cj. It is 3, 2, 0, m, 0, m. Okay, so for this 2m minus 3, so what is the column? This value will give you 2m minus 3 minus 2. So it is 2m minus 5. Next value is minus m. This is 0. This value is again 0. And this value is what? Minus m, uh, minus m, minus m, minus 2m, minus plus 3. Okay, and what is my solution? What is my z value? Z value is you multiply with this. So this is m plus 3. So you can see we have really improved our value from 3m, 3 times m to m plus 1. So say if my m is say 1 million, so the value of objective function was 3 million, but here it is 1 million and 3. So this is substantially small number as compared to the previous one. So I have improved my objective function. So I have to see whether I can improve further. So what I have to do here is again check for my zj minus cj. So you see here in case of z2 minus c2 is strictly positive, since z2 minus c2 is what? 2m minus 5, which is strictly positive. So optimality is still not attained. Okay, because one of the zj minus cj is positive. Remember that we are dealing with the minimization type problem, and for minimization all of them has to be negative. So that means I have to enter my x2 into the basis now. Okay, again I will go for the minimum ratio rule. So what is my minimum ratio rule? It gives me what? 1 upon 2 comma 2 upon 4 and 1 upon minus 1. I am not taking the negative of the value because the condition was that alpha j has to be positive. So this is 1 upon 2 again. So that means the minimum ratio is same at both the places. So I can enter anyone you desire, you can enter. Okay, so leave. So either S2 leave or XA leave. Okay, but I want my XA to leave. Why should I want my S2 to leave? So in this case, I will make my choice that XA should leave. Otherwise, in the next stage, you will have an option to leave XA. But okay, we have a choice. We will throw XA from the basis at this moment. Okay. So what that means my this number 2 is the pivot number. So what is my simplex table here? So I will write my table here. Again, one more thing I want to tell you, that you need not write this number, this column for xb. You can always cross this column. Why? Because I am not interested that xb to again enter into my basis, because xb was just in artificial variable I used to construct my initial basis. Okay, so similarly, once xa is out of the basis, I will cross the column for xa also. So I am not no more interested in this thing. Okay, so we have my variables as x1, x2, s1, okay, s2. Okay, so I am not again writing xa, but I tell you one more thing. If you need to calculate the inverse of the basis at some later stage, you need to calculate the values of xa and xpy, because the initial identity was under these columns. So if you are removing these columns at a later stage, you won't be able to calculate the inverse. So if in some problem you need to calculate the inverse, you need to calculate the values of xa and xp till the end of the problem. Okay, so what is my basis here? So my basis is again x2, s2, x1. Okay, and again my pivot is 2. I divide with 2, I get my value 0, 1, minus 1 by 2, and for s2 is 0, and right hand side is 1 by 2. Okay, now in order to make this 0, so I have to use this. So multiply this row by 2 and subtract from row 2. So this is 0. So what is my row operation? So row 2 is what? Row 2 minus 2 times row 1. So this is 0, and 0 minus 2 is plus 2, and it is 1, and this value is 0. Okay, uh, please mute yourself. Please mute yourself, anybody, so we on here. Okay, and for the last row, what you have to do is you divide this by 2 and add it to this one. So row 3 plus what? Row 1 by 2 is what you are going to row 3. Okay, so this value will become 1, this will become 0. So 0 plus minus 1 by 2 is minus 1 by 2, and for s2 it is 0, and 1 plus 1 by 2 is what? 3 by 2. Okay, clear? So again you calculate your zj minus cj. So what is your xb? So xb is what? Your sorry, the cost of your please somebody mute yourself. Okay, so what is the cost of these basic variables? As for x2 is 2, 0, and for x1 it is 3. So again we calculate zj minus cj. So it is 0, it is 0, it is 0, and for this one it is minus 1, minus 1, minus minus 2 by 2 minus 3 by 2 is minus 5 by 2. Okay, so you see I got a basis with my original variables, and my zj minus cj's are all less than or equal to 0. So you can see since zj minus cj is less than or equal to 0 for all j, so the present table is optimal. Okay, with optimal solution as what? X1 is 3 by 2, x2 as 1 by 2, s1 as 0, and s2 as also 0. You can see this is a degenerate solution because 3 variables are in the basis and one of the variable is taking 0 value. So optimal, this is my optimal solution, and in fact I must write that this is a uh, degenerate PFS, just for your information. Okay, and the objective function value is what? Z is what? You multiply CB with XB. So this is 2 by 2 plus 9 by 2 is 11 by 2. So 11 by 2 is the objective function value. Okay, so what we did, we were able to remove our artificial variables from the basis by appropriate choice of their coefficients in the objective function. Okay. In case of maximization problem, take minus m instead of capital M as cost of artificial variables. Okay.